Okay, so thank you, Ricardo, for here today with us. We can start.
Okay, well, thank you very much for the introduction and for the kind invitation. It's always a pleasure for me to be here at UPM. My name is Ricardo Vinuesa. I work at the KTH in Stockholm at the Department of Engineering Mechanics. I'm going to tell you some of the developments that we have been doing in my group on modeling and controlling turbulent flows through deep learning. So we're going to talk about the CFD and machine learning techniques. And my research is funded mostly by CERC and a number of foundations, including the Lundquist Foundation that enables this type of activities. So I think I need to change manually. There we go. Okay. So a little bit of introduction. I mean, we all know that machine learning has witnessed a number of success stories where perhaps image classification is one of the most typical examples in the context of the ImageNet challenge, where when you want to identify objects in pictures, machines are much better than humans. Machines make only 2% errors, whereas we are having much higher rates of failure of around 5%. So there are many areas, speech prediction, financial applications, where machine learning can really help and can really help us to develop more efficient solutions. And perhaps if we want to go back some years ago and look at tasks where machines can obtain superhuman performance, so they can really perform better in very narrow tasks than humans, maybe we can look at the game between the IBM machine Deep Blue, who played chess against the champion at the time, Garry Kasparov. This is 1997, and well, it turns out that the machine was able to defeat Kasparov. He didn't take it that well, to be honest. He was a little bit upset about it, and there are some fun stories that you can read about. But the point is that chess is a quite easy game to play. I mean, essentially, through brute force computing, you can evaluate many possibilities, see which one is the most beneficial, and then go in that direction. There are other games that are more difficult for a machine, for an algorithm to learn how to play. And I'm sure many of you have heard about the game of Go that has become very popular thanks to DeepMind. And if you essentially take the number of possible moves in one turn and you raise it to the power of the number of turns that you have in a typical game, then you can define the complexity of a game. And if you compare these two numbers, what you see is that Go is many orders of magnitude much more complex than the game of chess. So to play Go is not just enough to evaluate many possibilities and take the best one. You need to develop some sort of strategic thinking, some sort of intuition to kind of be able to perform in this task. And what we have also experienced is that some years ago, 2016, the DeepMind team from Google, they were able to develop an algorithm that learned how to play Go by watching the best, by basically getting information from the best human games. And essentially, through that, it was able to learn the best strategies, and they confronted this algorithm with Lee Sedol, who was the world champion of Go at the time, and the machine won by 4 against 1. So that was actually quite remarkable, because it was expected that machine learning algorithms would reach this the capacity of playing Go in many decades, and when it was achieved now 6 years ago, it was quite a surprise or quite an achievement for this type of algorithms. By the way, these algorithms, they are based, the ones that are playing Go, the one that I'm going to discuss now in a second, they're based on what is called reinforcement learning. And I will get back to that later in the seminar, because we're using that for fluid mechanics problems. What they did afterwards is even more impressive, I think, and it's that they developed an algorithm called AlphaGo 0, in which they did not show any human game to the machine. They just gave the rules of the game, then the algorithm played against itself, and doing that, it was able to develop the best strategies to be able to win at this game. And what I'm showing here is the score that the machine was getting. This horizontal line was the performance of the human-trained machine, and training against itself in less than 48 hours, this algorithm was able to get a better performance than the best human players, essentially. So in less than 2 days playing against itself, this algorithm was able to achieve a superhuman performance. And what is more interesting is that it did not get any information from the human games. So it was able to develop novel strategies basically on its own. No? So it's actually quite promising in the context of machine learning that we can get many different areas that can have positive benefits of this technology. We have a recent review, you can see it here in Nature Communications, a couple of years ago, where we saw for all the SDGs, the Sustainable Development Goals of the United Nations, what was the potential, both positive and negative, of machine learning, deep learning methods. And we saw that 79% of the SDG targets could be positively affected by AI, where the environment has a quite positive potential, and perhaps the society can have some negative effects, which we are all very well aware of. So there is quite some potential in a very wide range of areas. The SDGs are very broad. In particular, I would argue that the issue of interpretability is essential. Deep learning models, as many of you are aware of, are not interpretable. They're essentially black boxes where you are getting inputs and then you get outputs, but it's very difficult to really know what's going on inside. And then what we advocate for is the usage of interpretability methods. So there is some work, and you can see we have a paper in Nature Machine Intelligence from last year where we look at these things. And you can also refer to Kramer and others, where you can actually get from the structure of the network symbolic equations that give you a pretty good idea of what the network is actually doing. And if you're going to use deep learning methods for applications that affect you in your daily life, then it should be interpretable, because otherwise you are in trouble, right? This, of course, has important implications in designs. Same thing if you want to control the flow, or if you want to design an algorithm to modify properties of the mechanism that you're working with, then you want it to be interpretable. Okay. So essentially, if you look at fluid mechanics, which is the main topic of today's talk, there are many areas where machine learning can really help. There is the pioneering work of Milan and Koumoutsakos 20 years ago, where they were able to model the near-world region of a turbulent channel with neural networks. There is work on subscale models for LES. There is work on definition of inflow and boundary conditions with machine learning, which can make potentially your simulations much more efficient. There is quite some work as well on trans modeling. Quite interesting, and I will also get back to it later in the talk. You can use what is called PINs, physics-informed neural networks, where you are using the government equations, the Navier-Stokes equations, to enhance your predictions and augment the data that you are collecting. And also in the context of flow control, there are many areas that are quite prominent, where machine learning can really give us alternative solutions and help us to get better performance. So here, what I will be discussing today is a number of problems within fluid mechanics that are related to control and modeling, where deep learning really helps us, and it can outperform traditional methods that have been deployed for this type of application. One of them is what we call non-intrusive sensing. Non-intrusive sensing, what it implies is that you have a flow. Let's imagine that you have a turbulent channel, and this is the wall, and you want to measure in the channel without disrupting the flow that you have in a certain region. And one possibility to do that is to measure at the wall, because the wall is not intrusive, and based on the wall measurements, you can predict what happens above the wall, right? And that's basically, why is that important? It's important for different reasons, but one of my motivations is closed loop control. Because if I know what's happening above the wall, then I can design an algorithm that can control the flow better. And it's much easier to measure at the wall than to measure on. So what we're going to do is to use some quantities that we can measure at the wall, and we're going to use deep learning methods to predict at different distances from the wall, which will, in a way, separate different types of scales that are going to be relevant to different types of control. Okay. And by the way, the details of this, you can see them in Guastoni and others. So this is the reference. Essentially, what we want to do is that we're going to obtain DNS data. We're going to conduct a direct numerical simulation. This example is a low Reynolds number, a 180 open channel. So in this case, for simplicity, because then we only have the dynamics of one wall, but this will apply also to a normal channel. So we have the symmetry condition at the upper boundary of the domain, and we're going to be using this DNS data to train a deep learning model so that we can do the non-intrusive sensing prediction. Okay. So in practice, what we do is that we're going to basically choose a deep learning model that is going to be beneficial to computer vision, because turbulence, for the ones who work with turbulence, is highly structured. You have a range of scales, you have a cascade of energy transfer. There is a hierarchy there, and there are very well-defined structures that one can try to exploit to make predictions in the flow. And what type of architecture is good for this? Well, on the top you have the typical fully iterative network, a multi-layer perceptron, where you have the disadvantage of having well, you cannot exploit any correlations in the data, spatial or temporal, because all the inputs are fed together to the network. There are more advanced architectures where you can actually exploit those correlations and then hopefully improve the predictions. There is another problem with these networks, and is that since all the neurons are connected to all the neurons of the next layers, then they have very high numbers of parameters, and that's not very helpful with images. With images, the standard, the simplest network that you can use is the convolutional neural network. Now there are more advanced architectures that we are also developing, but if you have a computer vision problem, the first thing that you do is to use a convolutional neural network to be able to see, because these convolutional neural networks, as you can see here, they're based on the convolution operations, right? So you have an input image that you can see here, you have a kernel, which is a 2D window, and then the convolution operation is going to give you as an output one value that is fed from many values of the input, depending on the size of the kernel. The advantage of that is that you can exploit the spatial correlations in the data that make up those features that are being picked up from the input data, so that you can have quite robust predictions. And the idea is that these networks are very widely used in computer vision because you don't feed the data all at once, like in a MLP, but you feed the data with a spatial location embedded in the input, right? So if there is something that has certain shape in the input, you can exploit that correlation to improve your prediction. Okay, so that's the idea of the convolutional neural networks. And going back to our example, we're going to take several quantities at the wall, which will be displayed over here. In fact, we're going to take 3 quantities at the wall. We're going to get the stringwise and spanwise wall shear stress plus the wall pressure. And we're going to predict at different planes above that wall the 3 velocity fluctuations, right? The stringwise, wall normal, and spanwise velocity fluctuations. And the connection between those 2 planes will be done through a convolutional neural network first. And then I will tell you about more complicated models. So how does this network work? What we have is, well, an input of 3 channels because we have 3 quantities. These inputs are images, which are taken from the DNS, depending on the Reynolds number, but for a low Reynolds number, you have 128 square grid points, but this can go up very quickly as you increase the Reynolds number. And the output is also 3 images with 3 channels, because you have 3 quantities that you want to predict. And remember, I take an input as which is an image, and the output is another image. And all of those images have features, and those features are going to be picked up by the network. So we have in this example 6 hidden layers. We have many different architectures, but I'm going to show you this one now. These numbers represent the number of feature maps that you have on each of the layers. So what this means is that in the first filter, I have a depth of, well, 2 or 3, depending on how many input channels, and I apply a total of 64 filters because I want to get 64 feature maps on that first convolution. What is interesting from this? Each of those filters or each of those feature maps are going to be centering, are going to be identifying different features of the input. For example, in the first layers, we could be looking at edges, we could be looking at circles, we could be looking at shapes that are very simple in that input. And as I go deeper into the network, what I'm going to do is that I'm going to hierarchically build more complicated features. I'm going to take those lines and those circles, and I'm going to build more difficult shapes based on the simpler ones, because convolutional networks are very good at learning hierarchically. So you get always that distribution. At the beginning, very simple things, very abstract things that progressively get into more complicated things. Not only that, they also get bigger. Let me say a couple of things before. They also get bigger because the receptive field gets larger as you go deeper into the network as well. So the first layers are seeing a small part of the domain, but with each convolution operation, the receptive field gets bigger and bigger, because of course, each point from the next layer has to receive information from many points of the previous one. So essentially, the predictions of the last layers are based on many more points from the input. So first layers are looking at very abstract and small things, last layers very complex and very large things. Okay. And that's a little bit how one can interpret the predictions of the CNN, the convolutional neural network. So one example that we have at Reynolds tau 550, this is again a two-band open channel. It's not a very high Reynolds number, but the advantage is that the Reynolds number is high enough, so you still start to have a scale separation. So you actually have meaningful turbulence, and therefore you can try to see how the predictions are changing when you are looking at the near wall region or the outer region and how those different scales are actually interacting there. All these results are published in JFM, so you can go to Wastoni and others and you can see everything that we have there. On the left, we have the three quantities of the wall, so the two wall shear stress components and the wall pressure. And on the right, we have the three velocity fluctuations at different wall normal locations, so different distances from the wall. Okay. Good. So in addition to, we have two methods to predict. What we can do, the easiest and more straightforward approach, is to use a fully convolutional network. So I take an image, which is the wall, and I directly predict another image, which is the plane above the wall. And that can be close to the wall or far from the wall, but just using a purely convolutional neural network. Okay? But we have also developed another method, which is based on first doing a POD, a proper orthogonal decomposition. So when you do a proper orthogonal decomposition, you separate the spatial temporal information of the flow into spatial modes, which are fixed, and temporal coefficients. And then if you use this FCM POD method, then you're only predicting the temporal coefficients. So you need to predict the spatial information. And that for some cases is helpful. We're going to look at it in a second. So we're going to see for which cases the FCM is helpful, for which cases the FCM POD is actually giving me a better performance. And you can find more information about the FCM POD also in this reference. So what I'm showing here is the stringwise wall shear stress fluctuations, so the instantaneous flow. The first column is at y plus 15, which is quite close to the wall. This is the heart of turbulence, the near wall region. And the second column is at y plus 100, so that's much farther away. Okay? And in that case, what you have is larger scales, and the physics is quite different from what you have, happen to have close to it. Now, the reference is the third row, and this is the DNS, so this is what we are trying to predict, essentially. The first row are predictions using extended POD, and the extended POD is formally equivalent to the linear stochastic estimation, so it's basically a linear method. And this is something important to recall. Turbulence is highly nonlinear, right? In fact, it has, if you look at the scale interaction, turbulence has one part which is linear, and that's what we call the superposition. You basically have very large scales which have their feet on the wall, and that footprint is essentially a linear process. So if you have a linear method to predict from the wall what happens above the wall, then you're going to be predicting the superposition. But there is another phenomenon, or a number of phenomena, which have to do with modulation. And the modulation is highly nonlinear and has to do with interactions among different frequencies, because it is a multi-frequency phenomenon. And that, of course, cannot be predicted by linear methods. If you look at the first row, so we are comparing this with this one, what we see is that the linear method, first of all, exhibits a strong attenuation of the fluctuations, and the colors are lighter, because much of the fluctuation happens because of nonlinear effects that cannot be captured. And the other thing that is interesting is that these elongated structures, which are the streaks, and when I was telling you before, turbulence has a structure, has a very well-defined structure. Well, that's what you can see, these streaky patterns that you can find in the flow. Those streaky patterns are very smooth, and they're much smoother than in the original data. And that's because the nonlinear phenomena give you that in a way, streaky behavior that is not so smooth. So those details that you can see here and you don't see here are basically nonlinear effects that have not been picked up by the linear prediction method. Okay. Now, the last row is the FCN, so the fully convolutional network, where I'm taking one image and I'm predicting another image. And what you can see is that at y plus 15, so close to the wall, we can basically nail the flow. We can get a very, very good prediction. So if you want to predict the flow close to the wall, based on information from the wall, that FCN method is the best. It's really, really very good. If you go farther away from the wall, so you are over here and you want to predict from here, what happens is that the data is much less correlated. So it's much farther away. There are many things happening in between. So the predictions are not going to be as good. However, if you compare the second row, the FCN POD with the DNS, what you see is that you still can get the location of the large scales. So those bands, you can actually get them quite well. You can actually get some of the nonlinearities, and you can get decent predictions with the FCN POD. Much better than with the purely FCN-based method. So what happens is that close to the wall is more beneficial to use just a fully convolutional network. Far away from the wall is much better to use an FCN combined with a POD. Okay, and this is confirmed if we look at the turbulence statistics. So what we have here is the string-wise, wall normal, and span-wise fluctuations. The orange is the FCN. The blue is the FCN POD, and the green is the extended POD, which is the linear method. And what you can see, for example, if you look at the U prime, that's close to the wall, well, we have less than 1% error. So we actually get the flow very well, very close to the wall. As we move farther away from the wall, and that's the horizontal axis, the blue dot starts to be better than the orange one, right? So far away from the wall, the FCN POD gives you a better representation of the flow, also statistically. And the reason for that, one could argue that far away from the wall, the physics is dominated by fewer large elements, by fewer large scales, which you can more or less efficiently encapsulate into a number of POD modes. Therefore, it's more efficient for the same capacity of the network, for the same predicting power, to just predict the temporal coefficients of these very large things than to try to predict everything at once. However, close to the wall, what happens is that the physics is much more diverse. You have a very wide range of scales. Things are less coherent. So to do a POD first and then predicting those POD modes is not really worth it, because you cannot really encapsulate efficiently the spatial information of those scales in a few POD modes. Okay, so close to the wall, FCN, far away from the wall, the POD is actually helping us. And POD, but now there are other methods also that one could actually use to make that prediction even more efficient. Okay. Now, something that I think is quite interesting is what we call transfer learning, right? So transfer learning, what it means is that you can use what you have learned in one scenario, in one problem, and use it in another problem. You can transfer that stuff that you have learned. So we have two examples of transfer learning. The first one is at low Reynolds number, so at Reynolds star 180, we train one network to predict at y plus 15. So basically from the wall to very close to the wall, we have that network. And now we want to predict at y plus 50. So basically we want to predict farther away from the wall. What we can do is to basically take the weights of the network that we use to predict close to the wall. We take the first three layers and we freeze them. So we use the same weights for 15 and 50, and we only train the three last layers. And why is that? Why do we think to do it like that? Because if you remember what I said before, the first layers of the network are identifying more abstract and simpler things, so basically smaller scales, and the last layers are looking at more complicated and larger scales, right? So here we have the underlying assumption that the small scales are similar, close and far away from the wall, and the larger scales, of course, are different. And if you compare the results with the case where the y plus 50 network was trained from completely, basically, then what you see is that we can get the same level of accuracy, so basically the same level of error, but we can reduce the training time by a factor of more than 4. So by transferring what we learn close to the wall to far away from the wall, we can actually save a lot of training time and training data, which is another important aspect of deep learning applications. We have another example of transfer learning, which is, I think, the most interesting one. And is, so we do the analysis at Reynolds star 180, so that's the Reynolds number. We train a network, and now we want to train another network to predict at 550, Reynolds star 550. What we can do is take all the weights from the Reynolds star 180 case, and then start the training at 550, not from random values, but from the values that I had at 180. So that in a way, I'm already closer to a good solution. And then I can try to see how that affects my training process. The idea, if we compare different characteristics of the training data set, is that I can actually obtain, by doing it like this, I can obtain the same results when I transfer the weights or when I start from random weights. I can get the same results, but I can reduce the training time again by a factor of 4. So basically, I can use 4 times less data at higher Reynolds numbers if I want to do the same prediction that I have. And why is this interesting? Well, if you think about it, the ones who know about DNS, you know, the 550 simulation is 7 orders of magnitude more expensive than the 180 simulation. So if I can do most of the training in a very cheap simulation and then reduce the cost of the high Reynolds number data by a factor of 4, that's quite good, right? That's quite convenient. So I can actually reduce the amount of training time. I can actually reduce as well the carbon footprint of the deep learning training process, which is another thing to keep in mind, right? Because if I need to train less, I need to produce less data, then that's quite beneficial. In fact, we should, if we know something about the problem that we're trying to model, that we're trying to predict, we should embed that information in our model. We should not learn the model, learn it, because we are wasting information and we are never going to get as good results, right? So if you're developing a machine learning model to do something and you know some stuff about that something, then that should be implemented in the machine learning model so that we can get better results and we can actually have a more efficient training. Okay, that's the case of transfer learning. Okay. Now, more predictions. So far, we have been focusing on the case where the input was one picture, right, from the DNS. So I basically know all the information from the input plane, and I was predicting an output plane. However, in reality, you don't have all the information. If you're going to do an experiment and you have some sensors, then you don't have such a fine representation of the flow at the wall or above the wall. What you typically have is a bunch of sensors, a matrix of sensors. But what you can do is use something to obtain a high resolution version of the input at the wall. And to do that, we are using what is called the generative adversarial networks, GANs, which are very good at these super resolution tasks. And GANs works as follows. What I have is a network with 2 parts. One part, which is the generator, and the generator is from the low resolution images is producing high resolution images, which are representative of the statistical features of the original high resolution images. And the discriminator has to decide if a particular high resolution image is real or it has been produced by the generator. Okay? And these 2 networks are trained together using game theory. So they are both getting progressively better at their own jobs. So I'm getting better and more realistic high resolution images from the low resolution ones. And the whole process can be seen here. I have my 3 low resolution inputs with the generator part of the GANs and producing high resolution wall information. So the stuff at the wall, from few sensors, I actually get a very densely populated plane. And then from this high resolution wall information, I can obtain high resolution information above it. Okay, so now I have from this, I get the planes with high resolution. And then what I'm showing you here is the stringwise Gaussian stress fluctuations of one instant. This is the DNS, so this is the reference. The first row is the result of taking this plane and downsampling, so basically reducing the resolution by a factor of 4, 8, or 16 in each direction. And what you can see here is that the case with most downsampling is actually extremely coarse. I mean, this picture over here has very little to do with the original one. You get very little information, which is what you will have in an experiment, by the way. And on the second row, I have the predictions. So I'm comparing these 3 little guys over here with the reference they have And what you can see is that the predictions, they're all looking very physical, very realistic. That's the point of GANs, that they look physical. And of course, if I increase the downsampling, the intensity of the fluctuations gets lower. However, they are always able to find the streaks, those long structures, right? I am having the right location of the streaks, the right sizes, the right spacing. And if I want to do flow control, I want to know where the streaks are. So actually this approach is pretty good at finding the right structures, at giving me physically looking images or representations of the flow, even from something as coarse as this. No? So this is actually quite interesting that from something like that, I can actually obtain this. Is quite encouraging. And by the way, all of these results, you can find them in WebMS and others. This is a paper from Physics of Fluids that we published last year. So all the details of the architecture are also there. And what we want to also do is, now that I know that I can reconstruct the wall information quite well, I can actually find predictions farther away from the wall. So I can actually have at y plus 15, 30, 50, and 100. Those are the different columns. The first row is the DNS, so that's the reference. And as I go down, I'm increasing the downsampling. No? So clearly, the most challenging prediction is going to be this one, right? Where I'm predicting with a very coarse input the data that is farthest away from the wall. And once again, of course, I have a lot of attenuation of the fluctuations, but I know where the large scales are, I know where the streaks are, I know where they are located, their spacing and their sizes. So it's actually an interesting prediction of the flow, which I can use for flow control eventually. We're able actually to use this quantity, because if we want to compare the performance on different databases with different resolutions, we could actually define a normalized downsampling factor, which takes into account a little bit how, because of course, if you have a coarser simulation and you downsample, then you have even less data. So you can use this quantity to have a decent representation of the downsampling among various databases. Okay. So if you want to predict with very coarse inputs, then GANs is a good approach because that allows you to obtain some super resolution. I'm not sure why this moved, but okay. Now, the next application that I'm going to talk about is about doing the opposite prediction. So far, I have been explaining you how we can take information at the wall, predict what happens above the wall. What I want to do now is take information above the wall and predict what happens closer to the wall. Okay. And why is that interesting? There are several applications where that's interesting, but one of them is what we call the definition of off-wall boundary conditions, which is quite popular in climate simulations and things like that. The ones who do DNS, or generally turbulent simulations, you know that most of the resolution is devoted to solving the physics close to the wall, right? Because that's where you have the smallest scales. But not only that, that's where you have also most of the production at, moderate Reynolds numbers. But of course, if you can, knowing what happens over here, predict what should be happening here, and you use that to set a boundary condition, then in principle, whatever happens below that point can be saved. You can have a much computationally cheaper simulation. Now, turns out that this is not so straightforward. I mean, this is ongoing work. But if I represent the error of the prediction as a function of delta y, where delta y is the distance between the input and the output, so delta y means that you are closer to the wall, then of course the error increases as I increase delta y. That's clear. And there are two challenges with this type of prediction as opposed to the previous one. The first one is the receptive field, right? Because when you are predicting close to the wall, you're using small things as an input, which fit in your receptive field. But when you predict far away from the wall, you have a very large scale, a very large structure, and your receptive field represents only a small part of that input. So I cannot very effectively exploit the initial information that I have as my input. The problem is the problem of missing scales. When you are predicting from the wall, it turns out that the large scales are having a footprint here that in a way is giving you information about modulation, about superposition. So you know a lot of these larger scales when you are looking at the wall. But when you do the opposite, when you try to use this information to predict what happens closer to the wall, then you don't have that information. So you are predicting with less information something richer in physics, right? So it's a bit more challenging. What you can do, if you look at our predictions, and this is, by the way, inspired also by work from Vinuesa Jimenez, where they did this simply by rescaling. So they have the plane here, and they just rescale to see what should be happening over here. We try to do that, but with convolutional neural networks. If you look at the results, this is my input plane at y plus 100. This is the reference at y plus 50. So this would be the boundary condition plane. And on the third row, you have the predictions. And you can actually see that the predictions are pretty good in principle, right? I mean, I'm able to actually construct most of the fluctuations, most of the details of the structures, but still, to make this work in a simulation, you would require a very, very detailed result at that input plane, which is not so straightforward to achieve. If we look at the spectra, for example, then what we see, the gray contours are the original spectra at y plus 50, and the orange ones are the predicted ones. What you see is that we are missing some of the smallest scales, right? I mean, the shortest and narrower scales are lost because you have a smaller receptive field and you don't have information for those scales. And overall, we get a 20% error, which, to be honest, is actually pretty good for this type of predictions. But to do it in the context of boundary conditions, one is to find alternative approaches. Some of those approaches which we're investigating include using, for example, max pooling in the first layers, because if you do that, you can bypass the problem of the small receptive field, and you can maybe use a more GANs-oriented approach to reproduce the small scales that are missing in my predicted fields. So those are directions that can be explored. And all the details of this can be found in this paper in arXiv. So this is also something that you can access if you're interested. And it's a direction that is quite promising as well for deep learning in order to enhance computer simulation. Okay. Another area which I think is quite interesting when using CNNs is modal decomposition. Okay. So if you do POD, the proper orthogonal composition, then you obtain a linear reconstruction of the flow where those modes are actually orthogonal. This is actually work together with Sole and some other colleagues, and you can see the article in arXiv here. What we decided to do was to use autoencoders. So the autoencoders are neural networks, which are in principle a bit boring because you have an image, you have a first part, which is the encoder, where you are applying progressive compressions of that image. And in the second part, which is the decoder, you recover the same image. So in principle, it's not so exciting, but it turns out that it's very exciting because the interesting thing is at the middle, in this bottleneck, which is what we call the latent space, then you have a very efficiently compressed version of the original data. And not only that, you get a compressed version of the data non-linearly because you are applying neural networks. And in that latent space, you can actually impose penalization, penalization properties of the model that you want to develop. So what we do is that we develop what is called a beta variation autoencoder, where we impose as a restriction in the latent space a penalization factor for the non-orthogonality of the modes. And why is that important? Because if the modes are entangled, then you're having physical phenomena which is mapped into different modes. Whereas if they're orthogonal, then you know that at least all the physics that is present in one mode is only belonging to that mode. And that's quite important for interpretability purposes. What we see here at the bottom is different autoencoder-based modal decomposition approaches, and we are showing the cross-correlation among modes. Okay. So of course, on the right, you have the POD, where we get 100% of orthogonality. That's pretty good. And the beta variation autoencoder is essentially orthogonal as well. We get 99.2% of orthogonality, which means that we have effectively managed to detangle those modes and get a quite efficient modal decomposition of the flow. In fact, this is a DNS of the flow in an urban environment, a turbulent flow in an urban environment. Here you have the reference, and here you have different autoencoder-based approaches with 5 modes. If you do POD, you reconstruct 32% of energy. And there are other autoencoder-based approaches that give us more reconstruction. But the beta variation autoencoder, which is the one that is orthogonal, gives us almost 90% of energy with only 5 modes. So we have managed to get a modal decomposition that is non-linear and that is orthogonal. And why is that interesting? Well, it's interesting because if you want to do POD of this case and build a reduced order model, a ROM, well, maybe you need 1,000 modes to get 90% of the energy, which means that you need to predict the temporal dynamics of 1,000 modes. But if you build it based on an autoencoder, you only need 5 modes. So then you only need to predict 5 temporal coefficients to build a reduced order model, which is orders of magnitude cheaper and simpler. So this, I think, has quite some potential in the context of model reduction, because turbulence is very complex, so you always want to reduce the dimensionality. And for reduced order models, it can really help you to develop more efficient control strategies later on. So this is something that can be quite promising. And then we have the area of pins, physics for neural networks, where we have also some collaborations with Esteban and some of the people attending the talk. So it's another area which is interesting. And we have an article where we apply pins to runs, to Reynolds average and reduction ratios. So what do? We take the 2D runs equations, the steady version of the runs equations, and we include the Reynolds stresses without any model. We just put the Reynolds stresses there because we want to avoid the inaccuracies associated with the eddy viscosity models, right? So we want to be able to just solve the runs equations and see what's the contribution of the Reynolds stresses. And the idea is that pins, the advantage of pins is that with respect to another numerical way of solving the equations, is that you don't need to solve the very fine gradients that you have to solve with other approaches. And why is that? This is because pins are based on automatic differentiation, which of course are embedded in the training process of the network itself. I mean, when you are getting the training, is just minimizing the loss function with respect to the weights that you are having in your network. So of course you need to do partial derivatives and apply the chain rule to do the training. Those partial derivatives, you can exploit them in the context of pins, because if you want to build the logarithm equations, you also need those partial derivatives, right? So the idea is that you have exact derivatives without having to solve the very fine details of the physics very close to the walls. And that, what it turns out, is that you have a computational cost that is very similar to that of an industrial run simulation, but you are not modeling those Reynolds stresses. So you have the potential of achieving much higher accuracy than with industrial ways of doing runs. Okay. And by the way, all these results are also in archive, so you can go for AVASI and others, and in this archive link, you can see all the results. The idea is that we need boundary data, okay, this red box over here. That's one of the requirements for this method. And then the physics for neural network methodology is based on minimizing the residual of the Navier-Stokes equations, in this case, the 2D runs, such that you are matching the boundary conditions, right? So that's the boundary conditions are what is guiding you towards the right solution of that particular representation of the flow in the 2D runs. The idea is that you can do this methodology in a wide range of cases of varying complexity. For example, if you can start with a simple Flanders scan boundary layer, which is a laminar pressure boundary layer that you can solve very easily, well, you can actually compare the reference and the prediction of the mean quantities, and you get less than 0.1%. So you can actually, a case that is trivial, you can trivially solve it with pins. So that's in principle a good starting. But more interestingly, you can go to turbulence cases. So this is a zero pressure and turbulent boundary up to Reynolds theta 7000. This is a DNS. So this is very detailed simulation. You can see the computational domain here. And now, because we are using the steady runs, what we can predict is the turbulence statistics. And we're not going to predict the instantaneous flow. We're actually working now on unsteady pins, and we have quite some progress on being able to predict the flow instantaneously with pins, which is pretty interesting. But for now, we're going to focus on the runs results, the steady runs results, which are the turbulence statistics. And what I'm showing here for a ZPG turbulent boundary layer is the comparison between the reference of the U, the V, and the Reynolds stress, and the prediction. And what you can see is that the mean flow has 1% error, which is pretty good. Even in the Reynolds stresses, we have less than 10% error. And you can compare here the inertial velocity profiles, the Reynolds stresses. I mean, in principle, we can predict quite well a two-rule boundary with a zero pressure gradient, which is a complicated flow case, with more accuracy than you would be able to have in a run-based simulation, a simulation. And the key is that we are not modeling the Reynolds stress; we are just solving it as part of the equation. More interestingly, if we go for more complex cases, for example, a two-rule boundary with a pressure gradient, in this case, you can see the information in Bobke and others in JFM. And this is, we have picked a boundary with a constant pressure gradient. So this is in near equilibrium. And the Reynolds theta gets to 3000, which is reasonably high for numerical data. And what you can see, this is a more challenging case because the flow is decelerated. So you actually get much more complex streamwise development. And you can see that the mean flow has an error of 0.3%. So we again nail the mean flow and we get very good representation of the skin friction, the shape factor, we also predict it pretty well. Even the Reynolds shear stress, we get it with less than 10% error, which again is a quite remarkable result because this is now a more complicated case. This is not something that you can so easily simulate with an industrial run. It's quite interesting if you compare the streamwise development of the boundary layer, even of the Reynolds stresses, because we can actually characterize pretty well the turbulence quantities and pretty much nail the Reynolds shear stress. And this is already a more complicated flow case. But we can even go for more complex cases. This is the turbulent boundary layer are on an airfoil, a NACA 4412 section. You can see the details of the simulation in Vinuesa and others. We had it in the Journal of Heat and Fluid Flow from some years ago. We have here a database of DNS-like resolution up to Reynolds number of 1 million, which, by the way, is what you can do in most wind tunnels. So we can actually do DNSs at quite high Reynolds numbers of winds. And we have picked a case of Reynolds number 200,000, where you can see the complexity of the flow that we are trying to model. And this is now something that with an industrial runs will start to get more challenging. So this is something that is not so clear that you will be able to predict reasonably well with industrial runs. And actually, what you see is that once again, these are the various Reynolds stresses. In the mean, we get 1.5% error. So we again are able to predict extremely well the mean flow. And even the Reynolds stresses, well, with around 10% error, which is something quite interesting because with industrial runs, we would not have a chance to get the Reynolds stresses nearly as close as what we can get here. We have a little bit of over prediction in the outer region because that's where the most complex physics is taking place. But still, we are able to get pretty good Reynolds stresses again at the cost of something that you can run on a laptop during a coffee break. I mean, this is something that is quite computationally cheap. Even more complicated is the case of the periodic hill. The periodic hill is one of those test cases that are very popular for modeling because it has separation, reattachment, complex 3D. Well, this is a periodic case, but still you get complex 3D structures. And also, it's a bit difficult also with the pressure gradient effects that are present in this flow case. What you can see here is the recirculation region. So the separation and reattachment that takes place around this valley that you can see here. And you can see that we are very good at predicting the separation and reattachment of the flow, even in this complex flow configuration. This is again something that a runs model would have a lot of trouble getting correct. The mean profiles are very well predicted, less than 3% error in the mean, and here the Reynolds stresses have higher errors on the order of 20%. But again, this is a quite complex flow case, which an industrial runs would not give you much from the perspective of the Reynolds stresses if you were to run this complex flow case. Okay. So this is when it comes to pins, there is quite some potential there to model runs and to model other areas that we're working on. And now, as I promised you at the beginning, we're going to talk about reinforcement learning. So I have some projects and some directions on using reinforcement learning for flow control, essentially. Reinforcement learning is a type of machine learning methodology in which you have an agent, which in this case would be our neural network. You have an environment, which would be the CFD solver, and that agent needs to be able to interact with the environment. Okay? So this agent does a number of actions on the environment, and those actions are in principle chosen randomly, but within a trust region. So you define a set of parameters that can be modified. And then the agent, well, it sets a number of actions on the environment. What that happens is that the environment changes, so the state of the environment changes. And the environment is also providing a reward. No? A reward is basically a measure of the quality of those actions under a certain norm, whatever the norm is. If you want to minimize the drag of an airplane, then the reward is minus the drag. Right? If you want to minimize the separation length, then that's your reward. Right? So you need to maximize a certain reward. And the point of the reinforcement learning is that the agent will interactively interact with the environment and will progressively converge towards a certain policy. Okay, and the policy pi is giving me for the number of actions AT subjected to a certain state of the environment ST, such that the reward is maximized. And that's the whole idea, that I can define my actions so I can maximize my reward. And this is something that we presented last year in the APS, and now we're working on several papers on this. The problem that we chose first is that of reducing the separation length of a 2D bubble, of a recirculation bubble. So we have a channel, a 2D channel. We impose suction and blowing, so we can separate and reattach the flow. And you have a control region upstream of that bubble, right? Now, what we can do in that control region is basically blowing and suction. So we can inject flow, or we can absorb flow from the main domain of the channel. And our reinforcement learning is defined as follows. We have a number of probes, which are these orange dots. Here we have the flow. So the color region is the one with negative velocity. So that's the bubble that you can see there. And the reward is this arrow, basically, so it's the length of the separation bubble. And in this green square over here, I'm setting the actuation. And the actuation is modeled as a volume forcing, but this could also be done with a boundary condition, with blowing and suction velocities at the wall. And what I'm doing is that I'm essentially trying to introduce positive or negative velocities upstream of the bubble to be able to perturb it and minimize the separation. For this problem, the usual approach is to do periodic forcing. So you basically look at the most unstable modes or the least stable frequencies of the flow, and you force with that frequency. And the idea is that the reinforcement learning would hopefully come up with something a bit more sophisticated, a bit more complex. What you can see here is that in principle, there is like a two-mode type of control, a high frequency one, which gives you these wave packets that you see here, but there is another time scale associated with the length of the bubble that seems to regulate the, well, how often those pulses are being sent. Okay? And here I'm showing you the bubble reduction as a function of the time step for a certain episode. The periodic forcing, which is the baseline, is the black line, and the PPO, that's the approximate policy optimization, that's the DRL, is the blue line. On average, the DRL performs better than the periodic forcing. The periodic forcing gives us around 20% reduction of the separation length, whereas the DRL gives us around 30%. This is for a very low amplitude of the control. So if we increase the amplitude of the control, in principle, those differences will increase. But for this small test case, DRL seems to be quite promising because it's giving us novel control strategies that, in principle, are going beyond what can be achieved with classical methods of flow control. Okay. And that's my conclusions. This is a summary of the various topics that I have told you about. Here you have my information, my email, the web of my group, vinuesalab.com, and also my social media information. So if you have any questions and you want to collaborate or discuss something, or you have curiosity about something, feel free to contact me, because I'm always very happy to discuss and to talk about things. And for now, I'd like to thank you very much for your attention, and I will take your questions. Thank you.
Thank you very much. That was very, very nice talk. I don't know if you have any questions. Seba?
I have three. I wasn't taking notes because I have a lot of stuff. Right, so regarding the first one, we do the extrapolation from the inner wall towards the outer layer. So I was wondering, supposedly an extrapolation, so if you want to predict the mean quantities, for example, I would guess that a logarithmic extrapolation would be adequate because we know things go logarithmic. And regarding the random stresses, we know the shape, no? The exact shape is that one you show. So could we use this shape to do the extrapolation as opposed to using a non-linear line?
So there are some things here, and the first one is that I want an instantaneous prediction. So to make that prediction, it's not enough with just getting the mean quantity, not the time average quantity, because what I want to do is for a certain instant, I want to sense at the wall what is happening, predict what the large or small scales are doing at that instant, and then instantaneously define the control for that particular state of the flow. So I want an instantaneous prediction of what is happening, and of course, all these arguments are based on the average statistics. However, something that is an idea that we are exploring is to take some of the known information, for example, a linear method, the extended POD, that gives you part of the physics, use a linear method first, and then use a neural network to predict the remaining flow that has not been predicted linearly, or maybe if you want to do it statistically, to know something about the flow, you remove part of the prediction, and whatever is left is basically non-linear stuff that you can then predict efficiently with the neural network. So that's something that we are exploring, and yeah, we're still working on it, but it's something that could be helping. But essentially, the key is that you want an instantaneous prediction. Yeah.
Okay.
There is something in the chat. I don't know if.
No, it's me that I said.
Okay. Then there is nothing in the chat.
So then when you go from the outer layers towards the wall, try to find a sort of model like this still needs training, right? So you still need information near the wall. So that doesn't completely avoid the use of a fine mesh and all that stuff. So what's the idea there?
Yeah, the idea, that's of course our question. The idea is to explore the feasibility of these methods. First, you would do it in a channel, and then you would do the mapping, and you need a DNS of a channel to do that in another configuration. But what could be is that then you might be able to do some transfer learning later on. You train things in a channel, you want to do a wing, then you might still need a DNS of a wing, but you would do it with very little data to complement that training that has not been present in the simple one. I have to say another thing, and is that this approach, this was just a proof of concept of mapping and the boundary conditions and motivation for the proof of concept. But if we do this in a code, we would not do it like this. We would not take what happens above the wall, scale or predict, and then see what happens closer to the wall. Because what you have in an alias, it would not be a filtered DNS, it would be something quite different. So my feeling for this, and this is ongoing work, open to collaboration if you guys are interested, is that what you need is not the perfect DNS-based prediction at that instant, but something more physics guided, or something that statistically will be correct, like something like what will be the time average on that region plus some V prime fluctuations at that location. So something more nuanced, what you would need there to work in a code, not just because there have been some attempts of doing that, just taking the DNS. You just take the DNS plane at that location, you do it, and that doesn't work because then you don't have a filter DNS, you have an ADS, which is different. So yeah, there are some ideas that need to be explored to make that work. But in principle, your original question for new geometries, transfer learning will be one of the areas.
Javier Jimenez said that they cannot hear Esteban, so you can repeat the question before.
Yes, the question was, well, if I remember, the first question or the second one?
Both of them. And now the third one.
And then the third one, I will repeat it. No, well, the first question was that the prediction, if you could use the statistical quantities to improve the prediction from the wall to far away from the wall. And my answer was that the predictions are instantaneous. So in principle, those statistical quantities, they wouldn't help for instantaneous predictions, although one can use some known information about the flow to improve those predictions. And the second one was about the boundary condition.
Near the wall to train the.
Yeah, no, exactly. If for the off-wall boundary condition, of course, you still need the data to set up the boundary condition close to the wall. And my answer was that, of course, you need to either do transfer learning to take a simple geometry and then use that data for a more complicated geometry. And anyway, one needs something better than this to make an LES work. I mean, you need something statistically consistent or predict something that the V prime fluctuation is coherent with the flow. So it's more complicated than that. And this is just a simple approach to it, but a first step in that direction. And now when you make the third one, I will repeat it. And then, yeah.
Maybe I can go there.
Maybe you can sit here and we can have some coffee and discussion.
The last one is why I don't see why the pins doesn't get the fluctuations right, more or worse than the mean quantities. To me, it's another variable, and it's imposed by the boundary condition. So I don't see why the errors are larger in this.
Yeah, that's an open question. You're totally right. I think because of course the relative weight of the different quantities is different, no? To minimize the residual, but it seems that probably the mean quantities are having a bigger weight towards the physics in a mean sense of those cases, and maybe that's why you get a smaller error. But it's true that it's not fully clear the reason. And of course, we are completely relying on the quality of the boundary conditions. If your boundary conditions of the non-stresses are garbage, then you will get garbage. So it's, let's say, a quite new direction.
So this, but what define these boundary conditions?
They're taken from the DNS.
They should be right.
They should be right, but if the quantities of the mean are larger and more relevant to the physics, then probably they will be prioritized in the minimization process of the residual to get a decent prediction there. But again, this is still not fully known, let's say.
Very nice.
Thank you very much, Esteban, and very nice questions. There is some stuff in the chat also. Graciano Carrillo, I have a question about pins for runs.
Hi, I don't know, you hear me?
I hear you.
Okay. No, because it's about the use of pins, because in some cases there is like problems with the pins in the stability because there are like a fight between the loss functions for the boundary and for the other positions, let's say, and then there are local minimums, and then you don't get a proper solution. And I see that you do. My question is, did you find any problems of using pins in these situations?
Yeah, no, it's true that it's not fully obvious how to train them. To be honest, for these study cases, we didn't really experience problems or many problems. The most challenging is when you're having unsteady equations that you want to model with pins. Then when you enter the temporal dynamics, then things get quite complicated. And this approach doesn't work in time. You need to have the time information in another way, solve that, and then make it consistent with the spatial one. So in our experience, the most challenging is when you go into the temporal dynamics.
Yeah, okay. Because I saw like, some people is applying some automatic scaling of the different loss functions just to make the training more stable. And I guess, as you say, in this simple scenario, it doesn't happen. But yeah, it could happen.
For the study case, it's reasonably simple because the boundary, I mean, there are two losses: the boundary conditions, which you need to fulfill, and then the residual of the Navier-Stokes. And then, of course, things are of the same magnitude, just by the definition of the equations, so you don't need rescaling. But then in time, things get more difficult, and probably in other problems, things are even more difficult. Yeah.
Okay, thank you.
Thank you very much.
Welcome.
Ricardo, you have Javier?
Yes. Javier, you can unmute yourself.
Okay, yes. Yeah, I have a question.
Yeah.
I mean, I think it was around the slide number 24. You were finishing with channels.
Go there.
And then you were trying to estimate the boundary condition from the off-wall plane.
Yes.
How do you know there that the wall is not rough or has ribbles or has
Yeah, no, that's another question. Of course, we didn't consider that. I mean, this is just a smooth channel, a simple channel. But if one were to develop something general enough for rough walls and dribbles and things like that, then you would need to consider that in the model. And probably you have either some transfer learning or even a more complex model that accounts for that. So yeah, that's not something that we are considering in this yet, but of course it's a very good point.
But I mean, my question is, how do you know that you are doing a smooth channel? Where are you putting that information in your?
Currently, this is a purely supervised learning case. So I am using information of a smooth channel, and I'm trying to reproduce that one. In principle, if you are having this in general, you don't know it. So you would have to know from the large scales something that gives you, somehow the information that this is going to be predicted for a rough channel, or including that explicitly in the model, maybe with some classification step before, so you know the type of flow that you're doing, and then you're training different models that essentially gives you a different set of parameters. So yeah, that's basically future work. It's not clear.
The idea is that you don't know that. I mean, you don't know that from the outside, as Townsend model, and it seems to work quite well. I mean, when you are away from the wall, you don't know whether the wall is rough or not. You only know that when you are at the wall or in the near wall region. And if you throw that away, then you just don't know it. You cannot use that because you don't know it.
No, you don't know it from the data. Of course, you don't know it. I mean, it would have to be that you know that you want to simulate a rough channel or whatever, and then you are, classifying a model with particular parameters for those cases or something like that.
I see.
Yeah.
Okay. Thank you.
Thank you. But I mean, again, this is something that will have to be explored. I mean, this is a very good question. Thanks.
I was wondering in the work, is there any work related to instead of using the differential equation, try to use conservation equations or a weight formulation of those?
Yeah, that's a good question. I think. The question is if instead of using the governing equation, if there is some work of just using some conservation equation or some weak formulation or something like that. I think that Karniarakis has published something in that direction, and I think they call it physics guided or something like that. It has kind of like a different name. So there is some work there, and certainly something to look into. Yeah, we haven't looked at it ourselves. Yes.
Regarding the reinforcement learning, the TPO model, how do you model the reward function? Because I have tried this kind of architecture, and I found quite challenging, and modeling the reward. It's just a linear function, or?
Yeah, the question is for the reinforcement learning, how do we model the reward function? Of course, the challenge here is that you have an action and then the flow is changing, but you want something in the statistical sense to be optimized, right? We have a moving average that you have the time scale of the flow, which is connected with the time scale of the control. And then you also have a characteristic time of that moving average to kind of see, and of course you cannot get converged statistics for each action because this case is quite simple, but when you go to turbulence, we are doing now this in turbulent channels, well, then you cannot wait for things to converge in order to get, so you need to get some short-term averages to define your reward such that you can have an assessment of how good the actions were before choosing the next actions. And that's a little bit at the moment of manual empirical assessment because each case is a bit different, but one can do it with moving averages.
More questions?
Let me see if here there are more.
Okay, I also have 3 questions. But
Perfect.
I can discuss with it. In the last day that you have presented.
In the last.
Yes, you apply.
Yeah. Let me go there.
And do you need to have a clear idea about some passive control mechanisms where to actuate?
Yeah, I mean, here we make the active choice of where we want to actuate. So we know how the flow is going to behave. I mean, of course, it's good to have some baseline, so some classical control that can give you an idea of what you want to do, and then that guides where you have to, how you have to decide your agent and the properties of your agent. In the case of turbulence, we are doing now, we are mimicking a position control, for example. So you know, in fact, what we are doing for turbulence is that you take a established control and then what you learn is a residual with respect to that control, which kind of helps you to have a good starting point for the reinforcement learning. So certainly, whatever you know about the case and how to control it is going to help you.
Okay. Okay. The second question is, well, in human flow, you cannot perfectly predict something. You always need to assume an error. How do you quantify the error? Are you satisfied with prediction of the higher than statistics, lower than statistics, retrospective? What do you do?
Yeah, the question is that how do I quantify the error in turbulence, in the turbulent predictions? And I mean, in this, it all depends on your application. My non-intrusive sensing is aimed at doing flow control. So I'm interested in having good instantaneous predictions. And then what I get is the mean square error of the fields that I want to predict on all the snapshots that I am considering. In that direction, something that can be interesting, and that's something that I have discussed with some people recently, is to introduce some statistical restrictions on your predictions to make sure that the flow is physical. So some skewness, some flatness, some symmetries of the flow that need to be satisfied that perhaps can also be included as a penalization in your predictions. But for now, I'm interested in instantaneous predictions, so it's the mean square error of the instantaneous ones. But of course, that can be maybe refined with more statistical quantities.
Okay, thank you. And the last question is more technical, but I'm also interested in your opinion. Because when you define the neural networks, do you think that it's better to define this network based on experience, or it's better to use hyperparameter approach?
Yeah, the question is how to decide the architecture of the neural networks from experience, or how to set up the hyperparameters. I mean, in principle, we have gathered now some experience, and we know a little bit of how to decide these architectures. But for example, in the case of the CNN, we started with that architecture of 6 hidden layers and a certain capacity per layer, because that's what is generally used for computer vision problems of that size. But later on, this is something that I haven't shown today, but we have realized that for turbulence, it's much better to have much deeper networks with fewer parameters per layer. So, which makes sense, of course, because turbulence is highly hierarchical, right? So you want to have the possibility, after many convolutions, to build very complicated things, even if you don't have so many parameters in each of those layers. So for the same number of parameters, instead of 6 hidden layers, if you have 30 or 40, and again, the number of parameters is the same, so the cost is the same, the predictions are much better. I mean, you can get improvements by a factor of 4 or 5 in the error. So we start from architectures that are existing for computer vision problems, and then we try to learn how to adapt them to our particular turbulence problems.
And are there architecture problems? I think, for example, the case that you saw where you present some prediction on the turbulence flow, the different ways. Can you use the same architecture to predict something else?
The question is if the architectures are robust, if we can use the same architectures for different flow cases. And for example, the case of the very deep network, we went in that direction when we started to predict boundary layers instead of channels, right? So now it's a different case. It's quite similar in principle, but it's especially developing. So my guess is that when you go to more complicated things, pressure and boundary layers in wings and things like that, probably you will have to change the architecture or start with some transfer learning first, and then you will probably need to add some additional mechanisms to understand the complex large-scale interactions. Maybe it has to be an even deeper network, or maybe you need to start to do skip connections. So it's possible that more complicated things will require more complicated architectures, but that's something that we will know when we start to get there.
Okay, thank you very much.
But no, those are very good points, of course.
Thank you. No? Okay, so thank you very much again. Very nice talk, very interesting.
Thank you very much for the invitation.
Thank you for accepting the invitation.
Okay, yeah, well, thank you very much. And again, I'll be around today, and you have my information here. So if you want to ask more things, you can send me an email or a message, and I'll be very happy to discuss more. Yeah, thank you very much.
Thank you.